All right, so this is the video for the practice problems for kinematics, or Unit 1 as it's known in AP Classroom. So we have a cylindrical object which can roll down some incline as shown in Figure 1. The incline is slightly less than 1 meter long. A group of students wants to determine the acceleration of the object as it rolls down the incline, and the student have access to the following equipment. Okay. So, we want to assume that the object moves with a constant acceleration. All right, let me just switch my pen. A constant acceleration as it rolls down the incline. Write an equation that includes acceleration and quantities that can be measured or obtained from measurements by using the available equipment. So, using the available equipment, it looks like we can measure changes in position and time. Now, if you remember, the initial velocity of this is likely going to be 0 because we're going to start this object at rest. Now, we need an equation that has those variables and only those, and that's going to be the position versus time equation. So, delta x, which is just x minus x0, is v0t plus 1/2 at squared. So, delta x is 1/2 at squared. So acceleration is 2 times delta x over t squared. Okay. All right, so let's check the scoring guide for that to see how I did. So the scoring guide is going to be over here somewhere. So it looks like I get 1 point for a valid equation that includes acceleration and conceptually relevant, and for stating or implying that the initial speed is 0. So I have both of those things because there's their example response. I just rearranged for the acceleration. So I got 2 points there. Next, I need to design an experimental procedure that the students could use to measure the quantities required. In the table below, list the quantities and associated symbol. Also list the equipment that would be used to measure each quantity. So the quantity to be measured, which would be the change in position. Okay, so I'm going to use delta x. Now I have 2 different things that would allow me to figure out a change in position. A pair of calipers or a meter stick. Being that the meter stick is 1 meter in length, I'm probably going to use the meter stick, because that is closest to the distance that this object would be traveling. The next thing I want to measure is the time, and that's going to be represented with a variable t. Now I have a stopwatch or a clock. This object that's traveling down the incline is likely not going to travel for a whole entire minute. So that's why the stopwatch is the better choice. Okay? So those are really the only 2 things I need to measure to find the acceleration. Okay. So we want to describe an overall procedure, provide enough detail, including steps to reduce experimental uncertainty. As needed, use the symbols defined in the table and or include a a diagram. Okay, so I would say first, pick a starting position of the ball of 20 centimeters. So, like, this would be 20 centimeters. Okay. Release the ball from rest and measure the time to reach the bottom of the incline. Okay. Then we're going to repeat for 3 trials to find T average. So the average time it takes to get down. Okay. Then you're going to repeat 1 through 3 at other positions. Okay? So we have something that measures delta x. We have something that measures t. We're getting rid of experimental uncertainty. Wonderful. So C then says, what quantities could be graphed? Oh, wait, let me score myself for B. So let's see. For B, I get 1 point for listing relevant and appropriate equipment that matches the measured quantities. So their example were stopwatch, meter stick, position, and time. So I got that. I get a plausible, practical way to directly measure the acceleration. Okay, I did that. Measuring the position of the object at equal time intervals. So I'm measuring the time for different positions. So I think that this, even though I did it differently, I feel like I would still get a point for that. I would give you guys a point if you had said this. But they're saying mark off distances. Oh, yeah, okay. So their example 2 response is exactly what I said. So I get that point. So I get all 4 points. Whew, scared myself for a second. All right. So what quantities could be graphed to yield a straight line that could determine the acceleration of the object? Only indicate quantities that were either measured in part B or could be determined from part B. So remember, our acceleration equation for this problem is 2 delta x over t. So that actually gives us a slope, okay, because we have a division occurring. If we had multiplication, then that would be an area. Remember, slope is change in y over change in x. So that tells us that we should graph 2 delta x on the vertical axis and t squared on the horizontal axis. Okay? The slope of the graph would yield the acceleration, as acceleration is 2 delta x over t squared. Okay. Let's score myself for that part. All right. So I get 1 point for choosing appropriate quantities. So 2x and t squared, like I said. So I get that 1 point. And then I get 1 point for indicating that it could be the slope and for correctly indicating how the acceleration could be determined from the slope. Okay, so I said just use the slope because acceleration is that 2 delta x over t squared. All right, now part D. After rolling down the incline, the cylindrical object rolls across a horizontal surface, as shown in figure 2a. The object then hits a vertical wall and bounces off with the same speed it had before. So this speed and this speed are the same. Note that during the bounce, the object is in contact with the wall for a time interval that is very small, but not 0. On the dot, which represents the object during the time it's in contact with the wall, so this part here, draw an arrow showing the direction of the object's acceleration. Okay, so the direction of the acceleration is going to be the same direction as the force exerted by the wall. So the wall, in order to change the ball's velocity from moving right to left, has to exert a leftward force. So we should have a leftward acceleration. All right. So during the time that the object is in contact with the wall, is the magnitude of the acceleration greater than, less than, or the same as it was while it was rolling down the ramp? Okay, briefly explain your reasoning. Okay, so we have a change in direction here. Okay, so in this time period to get down the ramp, our acceleration is just going to be A equals delta V over T. Okay, but our initial velocity is 0. So our change in velocity is really just V, that speed at the bottom of the ramp, over T. Our acceleration when we hit the wall is again going to be delta v over t, but this time t is very, very small. So we're dividing by a very, very small number. And in addition to dividing by a very, very small number, instead of doing v minus 0 like we did before, we're actually going to do negative v minus v, negative because we're moving leftwards, v because our initial velocity before we hit the wall was v, over that tiny t. So we have negative 2v over t. So not only do we have a larger change in velocity, we have a smaller amount of time. And both of those things are going to lead to a larger acceleration from the wall. So the acceleration is larger when the ball is in contact with the wall. This is because the change in velocity is larger at the wall, and this change in velocity occurs in less time, since A is change in velocity over time. The acceleration at the wall must be larger. All right, so let's check out my points for D. So I get 1 point for drawing an arrow to the left. Wonderful. And then for part D, I get 1 point for stating that contact time is less and for relating the acceleration to the time interval. So I mentioned both of that. Hooray, I get all of the points. All right, on to the next problem. So it looks like we have an astronaut throwing a ball straight up. So it looks like I have initial velocity of 15 meters a second. I have an initial position of 100 meters. I likely land on the ground. So my final position is 0 meters. I'm an astronaut, so I don't know if I'm on Earth. Nope, I'm on planet X, so I don't know my acceleration due to gravity quite yet. But if I was on Earth, the acceleration would be negative 9.8. So an astronaut holds a rock 100 meters above the surface of planet X. The rock is thrown upwards with a speed of 15 meters a second as shown. The rock reaches the ground 10 seconds after the ball is thrown. The atmosphere of planet X is negligible when the rock is in free fall. Okay, so that just means air resistance doesn't matter. All right, so we are asked to determine the acceleration due to gravity of the rock when it's on planet X. So I have an initial position, a final position, initial velocity time, and I need acceleration. So I'm going to use the position versus time equation. Plus v0t plus 1/2 at squared. Again, this is for question number A1. So my final position is when I'm on the ground, 0, and I'm going to use that final position because that's how long it takes me to reach the ground. My initial position is 100 meters, 15 meters a second, 10 seconds, plus 1/2 a 10 seconds squared. So this is 100 plus 150 is 1/2 a 100. So these two combine to give me 250, which I can then subtract from both sides. So negative 250 is, well, 1/2 times 100 is 50. And then I'm going to divide both sides by 50. Okay, so the acceleration is negative 5 meters a second squared. And remember that negative just tells us that the acceleration is downward, as we might expect. Okay, so how does the speed of the rock when it reaches the ground compared to the speed of the rock when it's thrown upwards. Okay. So this rock is going to follow a path, right? And it's going to rise up to some maximum height, let's call it h, and reach a vertical speed of 0. When it falls back down that same distance h, it will again have a speed of 15 meters a second, because remember, we have some symmetry occurring. However, the ball doesn't land there. The ball keeps falling, which means the ball continues to accelerate to some speed larger than 15 meters a second. Okay, so VD is going to be larger than VS. Okay. And I have to state my reasoning. Okay, so the ball will reach a negative 15 meters a second. I don't know why I wrote out negative instead of just writing it. We'll reach a negative 15 meters a second when it returns to the same height of the cliff after being thrown upwards. The ball then accelerates for an additional 100 meters, landing with a speed larger than 15 meters a second. Okay, so let's check my points for that. So for A1, I get 1 point for that 5 meters a second, but I got it. A2, I get 1 point for VD is greater than V up. Hooray. So when the rock, they say when the rock is thrown upwards, it eventually reach a maximum height as it falls back down to the ground. The same vertical height with which it was thrown will be 15 meters a second. So I started with the second sentence and then said, as the rock continues to fall or accelerate for an additional 100 meters, the rock speed increases above 15 meters a second. So I also got that 1 point. Okay. And then B, the student wants to know how the motion of the rock would be different if it was thrown upwards at 15 meters a second from a height of 100 meters above the Earth's surface. In a clear, coherent, paragraph-length response that might also contain figures or equations, explain the motion of the rock. In terms of maximum height, the speed at which it reaches the ground, and the time in which it is in free fall, and the acceleration due to gravity. So I have to mention all 4 of those things. So I'm going to write that over here. Okay, so some things to keep in mind on Earth is the acceleration due to gravity is about negative 10 meters a second squared. So I've doubled the acceleration due to gravity. Okay, so thinking back to that position versus time equation, t squared, right? If this first part here, essentially the change in x is the same, right? If this change in x is the same, and I'm increasing the acceleration, it makes sense that these time variables need to decrease. So we're going to have less time in the air. Okay. Also, because we have this larger acceleration, we're going to reach a lower maximum height. Okay. But the thing is, is even though we are in the air for less time and we reach a lower maximum height, that does not mean we are going to reach a smaller velocity before we hit the ground. Okay? So here's the person on Earth. We're still going to be thrown upwards with 15 meters a second. The only difference is we might not go as high. But the thing is, symmetry still exists. So we're still at 15 meters a second when we reach the cliff height for the second time. And then we still have an additional 100 meters to accelerate downwards with. Right? But instead of accelerating at 5 meters a second squared like we did on planet X, that acceleration is 10 meters a second squared downwards. Which means this speed right before we hit the ground is actually going to be greater because we're being pulled downwards with a larger force. Right, so we have a larger the ground. All right, so now I have to kind of write all of that in a paragraph. Okay, so I'm going to answer the question first. I'm going to mention these 4 things. So on Earth, the ball will have an acceleration of negative 10 meters a second squared. This will lead to less time in the air, less maximum height, and a greater speed when approaching the ground. Okay, so now we have to explain the whys. So let's talk about the time first. Okay, so on Earth, the total displacement, meaning start to finish, that's not how you spell displacement, displacement is the same along with the initial upward velocity. According to the position versus time equation, with those things held constant as acceleration increases, time must decrease. Okay, so we talked about why we did less time. Now we got to talk about why it's the lower maximum height. So the ball reaches a lower maximum height because according to v squared equals v0 squared plus 2a delta y, where v equals 0 and v0 equals 15, because the speed at the top is 0, we got to stop at the top. So where v equals 0 and v0 equals 15 for both Earth and X, as acceleration increases, delta y, or max height, must decrease. Decrease. Okay. So in these two sentences, I've included some background information and basic physics. So I've talked about what's the same for both things. And I've talked about the basic physics as far as like equations as to why, even though those things are the same, we're getting different times and different heights. Okay. So now for the larger V at the ground. Okay. So we can say just like in A, okay, I can reference things that I've already said. So I'm going to talk about this part. Okay. Just like in A, whoops, even on Earth, when the ball returns to the initial height after being thrown upward. Just like in A, even on Earth, when the ball returns to the initial height after being thrown upwards, it has a speed of 15 meters a second and 100 meters left to fall. However, because the acceleration is larger on Earth, the ball reaches a larger V ground than on planet X. Woo! All right. So I've talked about, let's just make sure I've talked about everything I need to talk about. Oops, it's not letting me zoom in. So I've talked about maximum height. I've talked about speed when we reach the ground. I've talked about time. I've talked about acceleration. Wonderful. All right, let's grade myself. So I get 1 point for indicating the acceleration due to gravity is greater. Yep, I said it's -10. I say that time is less. Awesome. Maximum distance is less. Awesome. Speed is greater. Awesome. And internally consistent. Okay. Wonderful. So the example response has a lot of the same things that I also mentioned, including this equation here. All right. So that is the end of this practice problem set. Have a wonderful rest of your day.